Section 9.1, Properties of Exponents. All right, in this section we're going to simplify some expressions, and as I do that I'm going to show you some properties of exponents. And some of these you may recognize what to do right away, but I'm going to work them out a little bit of a longer way at first to show you where the exponent rules come from and why they work, and then I'll show you the quick version afterwards. So if we look at x squared times x to the 7th, a lot of people know what to do there, that you should add the two exponents and get x to the 9th, but where does that come from? Well, if you think about what exponents mean, x squared means x times x, so that we have two factors of x, and then x to the 7th means 7 of those x's. 1, 2, 3, 4, 5, 6, 7 of them. And then if you look at what happens if you just write it out without the exponents, you have 2 x's, then 7 more, so you have 9 x's altogether. So kind of officially, that's what we would do there. We think we have 2 x's, then 7 more, that's a total of 9. But from that comes the rule that if you're multiplying two expressions where you have exponents and the bases are the same, you can just add the exponents. So the rule that comes out of this is that we should just do this as x to the 2 plus 7, which is x to the 9, but it just comes from this idea of that x squared means 2 x's and x to the 7th means 7 more, so a total of 9 of them. All right, on this next one, most people would look at this and say I should do 5 times 3, which is 15, and x to the 4th times x to the 5th, which is x to the 9th. And that is correct, but I just want to show you why that is okay, how that comes out of the rules that we've learned together. So if I rewrote this, let's see, using the associative property, we could say that because this is all multiplication, we don't really need those parentheses. And then using the commutative property of multiplication, we could say because this is all multiplication, we could reorder it and put the two constant factors first and the two variable factors near the end. And then using, again, the associative property, we could say we could do the 5 times 3 first, and then after that do the x to the 4th times x to the 5th piece. And if we do that, we get 15 from the 5 times 3, and the x to the 4th times x to the 5th, using this property right here of adding exponents, would be x to the 9th. But we don't want to work it out that slowly every time we do it. So what we do instead is just use this idea that if you're multiplying two monomials together, so no addition or subtraction, you can just multiply the two constant factors, and you can just multiply the two variable factors by adding exponents. So typically we would go straight to doing that. 5 times 3 is 15, and then x to the 4th times x to the 5th, add the exponents, 4 plus 5, and you get x to the 9th. So we'll go straight from here to here, but it's really a lot of use of the associative and commutative properties of multiplication that really allow us to get there. So on this next one, I'm just going to go ahead and show you that without going through the long way and just go straight to applying that rule. So I'll multiply the constant factors together, so 10 times 3 is 30. And then when you have more than one variable, multiply the like variables. So c to the 7th times c to the 5th would be c to the 7 plus 5, which would be c to the 12. And then on the d factors, we have d squared. And then when it's d here, that's d to the 1st, so that would be a plus 1. You could do that in your head and just do d to the 3rd, but I didn't want to show you that. That's considered a 1 exponent when there's nothing written there. And so then that would be 30 c to the 12th and d to the 3rd. And it's important to understand we can't combine these two because they have different bases. All right, and then moving on to this next one, if we just thought about what does 4x raised to the 3rd mean, an exponent means to take whatever the exponent is on, the base, and we would multiply that with itself until we had the exponent number of factors, or in this case 3 factors of that, so 4x times 4x times 4x. And then using the associative and commutative laws of multiplication, we could say that could be rearranged and regrouped so that it was the 3 4s times the 3 x's. And if we do that, the 3 4s is 64, and the 3 x's would be x raised to the 3rd power. So really some associative property and commutative property going on again to allow us to do that. But a lot of people look at that and they see a little trick they could do. They think, hey, maybe we could just distribute that exponent of 3 to both of the factors inside the parentheses, and it turns out that does work. So you'd have 4 to the third times x to the third, and then 4 to the third is 4 times 4 times 4, which works out to be 64, and x cubed. So that's a shortcut that we'll often use instead of writing it out this longer way. All right, let's continue on and see some other variations of these exponent rules in action. So we have w to the 8th over w to the 6th. So a lot of people will know the rule here, which is if you're dividing and the bases are the same, you can subtract the exponents. To tell you the truth, I like to think of it the long way all the time on this one, which is kind of a cancellation method. If there's 6 w's on the bottom, those should cancel 6 of the w's up top with 2 left over. So let me show you that this way. W to the 8th is w to the 6th times w to the squared. Think about our rule from up above. You would add exponents. That would get us straight back to w to the 8th. But I'm splitting it up that way so that you can see that the factor on the bottom, w to the 6th, has a match up top with the w to the 6th that's up there. And so we can cancel those. And then we get the w squared. So that's the way I actually always think of it. I might not write this out in the middle, but I would think these 6 w's on the bottom cancel 6 of the 8 up top, and there would be 2 left over. The other thing we could do is a subtraction rule for exponents, which again isn't the way I like to think of the cancellation method, but this is the other thing you could do. You could say take the base and take the top exponent minus the bottom exponent, and that 8 minus 6 will give you w squared. I just prefer this one because I'm kind of thinking it through instead of using the rule, and it doesn't really take longer, and I prefer to be able to think through something instead of having to memorize a rule for it. Alright, and then kind of like we distributed here, well not distributed, but like kind of group things by their likeness, constants and the same variable c and the same variable d, we can do the same thing if we're in a fraction. So I'm going to use this kind of cancellation idea here, and I'm going to show you everything I'm going to cancel. This could be something that's done mentally, but I want you to be able to see it. Between the 14 and the 21, there's a 7 in common. 14 is 2 times 7, and the 21 is 3 times 7. So I'll be able to cancel those 7s. There's 5 x's up top and 3 on the bottom, so I should be able to cancel 3 of them. So I'm going to show the 3 up top, and since there was 5 x's to begin with, there'd be 2 left over. And that should cancel with the 3 x's on the bottom. These 6 y's should cancel 6 of those, and that would leave 3 left over. So here's the 6 y's we're going to cancel, and here's the 3 left over to make that y to the 9th. And then we have the y to the 6th that was already on the bottom. And then we can go through and cancel things. This 7 will cancel, these x cubes will cancel, and the y to the 6's will cancel. And then we'll just write what's left over as a fraction. So in the numerator, we still have that 2. We have 2 x's and 3 y's. And in the bottom, all that's left is the 3. And I have a fraction bar that's too long, but there's my answer to that one. So you can actually jump straight from here to here, though if you did that, you would probably show a lot of like slash canceling. So maybe, and that can get kind of messy and hard for other people to read. So this is probably good to show, but if you want to just do it as slash canceling here, you could do that as well. I guess just showing you that real quick, you do things like 7 goes into 14 twice and into 21 3 times. These 3 x's would cancel 3 of those, and there'd be 2 left over. These 6 y's would cancel 6 of those, and there would be 3 left over, and then you just multiply the leftovers to get to here. But if somebody stumbles on and looks at that, it's kind of a mess, so this might show your work a little better. Either one's okay though. So 5 to the 0, I'd like you to just take a guess at that real quick. Like, what do you think 5 to the 0 is equal to? All right, so having given you a moment there, most people, or a lot of people anyways, if they haven't seen this before, would guess that 5 to the 0 would be 0, but it turns out that 5 to the 0 is defined to be 1. And I just want to show you kind of some logic for that. So first of all, let's just go ahead and write that answer down. So 5 to the 0 is 1. And let me just even show you that on the calculator to hopefully kind of convince you that that's true. So I would take just a 5 and raise it to the 0, and according to the calculator, that comes out to be a 1. So why would that be? So let me show you an example. Let's say we had 5 to the third over 5 to the third. If you just think about it, anything over itself should be 1. So if you have 5 to the third over 5 to the third, the answer to that should be 1. But if you use the exponent rule of subtraction from right here, then you'd say this is 5 to the 3 minus 3, which is 5 to the 0. And then you'd wonder, well, what is this? But we know these are all equal to each other, so according to this chain of equalities, 5 to the 0 would be equal to 1. So that's an argument that this makes sense. All right, so there's some examples of exponent properties in action, and we'll turn the page and go ahead and look at a summary of the properties that we've discovered as we work our way through this page. Alright, so we just worked through a bunch of examples and kind of discovered some exponent properties, and here's a summary of those. If n and m are counting numbers, then x to the m times x to the n, you can just add the exponents and keep the base the same. So in words, to multiply 2 powers of x, keep the base, add the exponents. Quick example, x to the third times x to the fifth would be x to the 8. And then we have the raising a product to a power rule. If you have two things in parentheses or more, if they're all multiplied inside and there's an exponent outside, you can distribute that exponent to each of the factors inside. So if we had something like xy to the fourth, then that can become x to the fourth, y to the fourth as an example. So in words, to raise a product to a power, raise each of the factors to a power. And then we have the quotient property for exponents. That's one of the ones we discovered on the previous page. It says if you're dividing two things that have the same base, you can just subtract the exponents. And we saw examples of that. So let's see, one would be maybe like x to the 9 over x to the 3 is x to the 9 minus 3, or x to the 6. And then we saw the definition of x to the 0 equals 1. We actually saw an example of 5 to the 0 equals 1. But they're claiming here that x to the 0 is almost always equal to 1. So if I wanted to use the example I used before, I could take like x to the 3 over x to the 3 and say that should be 1 because it's something over itself. And that should be x to the 3 minus 3 by the subtraction principle, which would be x to the 0. So I could claim these are all equal, and therefore x to the 0 equals 1. But there is one place where this bridge of equalities breaks down. This fraction, x to the 3 over x to the 3, would actually be undefined if x was 0. And so notice over here that part of the definition of a 0 exponent is that if you have x to the 0, it's 1 as long as x is not 0. 0 to the 0 is actually undefined. Alright, and then some other things that we'll be using, raising a quotient to a power. So if you have a fraction with an exponent on the outside, then to simplify that, you can distribute that exponent to the numerator and denominator. So something like x over y to the fifth could be rewritten as x to the fifth, y to the fifth. So in words, to raise a quotient to a power, raise both the numerator and the denominator to that power. And then the last property that we're going to summarize here is the raising a power to a power rule. We haven't actually encountered this one yet, so I'll show you an example of it. But if you have x to the m and you raise it to the n, that turns out to be x to the m times n, or in words, to raise a power to a power, keep the base the same and multiply the exponents. So an example might be something like x to the third raised to the second, and according to this, that would be x to the 3 times 2, which would be x to the 6. And since we didn't see that one on the previous page, let me just show you a quick example or work this out a different way to show you why that does work. X to the third squared, if you're squaring something, that means multiplying it with itself. And if you have x to the third times x to the third, you would add the exponents because the base is the same, and that would be x to the 6. And then we see that that does work out the same as if we just did the 2 times 3 to get the 6 right away. Alright, so there's a summary of the properties, and on the next page we'll start working through some more examples. Okay, so on the previous page we went over all the different rules for exponents, and we have those rules so that we can simplify expressions involving exponents. And this list here gives us some of the steps that we should think about when we're simplifying with exponents. So for something to be considered simplified, there can't be parentheses anymore. And if it's a monomial, one term, then each variable or constant appears as the base at most once. So for example, if you had an x cubed and times x to the fifth, you would want to combine that as x to the eighth. And then each numerical expression, such as 5 squared, should be calculated out, and each numerical fraction should be simplified or reduced. So let's go ahead and run through a few examples using the rules that we had on the previous page. So simplify each of the following, and the first one, part A, we have x to the fourth raised to the ninth. So this is one power raised to another power, so we use the power to a power rule, which says to multiply. So this should be x to the 4 times 9, or x to the 36. Moving on to part B, here we have 1, 2, 3 factors inside of the parentheses, and it's all being raised to the third power. So this would be our product to a power rule that says when you have multiple factors inside being raised to a power, you need to distribute that power to each one of those factors. One of the things people forget a lot is that the 2 is a factor, its own factor, so the 2 gets raised to the third, just like the x squared and the x to the seventh would. So this would be 2 to the third, x squared to the third, and x to the seventh to the third. So 2 to the third we'd want to work out. That's 2 times 2 times 2, which would be 8. So that would be an 8. And then we have x squared to the third, that's power to a power, so that would be x to the sixth. And again, power to a power, so 7 times 3 would be x to the 21. And then these are both the same base, so we'd want to combine that, and when you have two things with the same base and you're multiplying, you add their exponents together. So this would be 8x to the 27, where that 27 comes from adding those two exponents. And I'm going to go ahead and box that answer, but I'm going to come back to this, and I'm going to list it also as a B star. And I'm going to show you another way that that problem could have been done as well that might be a little faster or perhaps a little easier. So let me copy it again, 2x squared, x to the seventh, all raised to the third power. Instead of distributing right away, another option would be to work inside of parentheses first. Realize that we have these two with the same base and go ahead and combine them by adding their exponents. So that would be 2x to the ninth power. And we haven't done anything with the 3, so it would still be out there. And then we would raise each factor to that power, so we'd have 2 to the third, and x to the ninth to the third, and 2 to the third is 8, and x to the ninth to the third, we would multiply the one exponent with the other and get x to the 27th. Same answer as we got before. So those are both equally fine options. You could do either one. You could distribute first and then combine the like bases later, or you could combine the like bases right away and distribute the power of 3 later. Just really up to you. I wouldn't argue one over the other. Alright, let's look at part C. So 18y to the 10th over 24y to the 4th y to the 6th. This time I'm going to go ahead and take the tact of combining these two first. So I see the two different y's with the same base, so I'm going to simplify those. And while I do that, I happen to notice that the 18 and the 24 have a 6 in common. So I'm going to rewrite that 18 so I can see the 6. So 3 times 6, and then I have a y to the 10th. I'm going to make that 6 show up in the 24 also. That's 4 times 6. And then when I combine these two, they have the same base, so I add exponents, and I get y to the 4 plus 6, which would be to the 10th. So I'm going to cancel that 6 that I noticed a moment ago and revealed when I factored, so that those can cancel off. And this wasn't necessarily the goal when I combine these two, but it turns out that it matches up with the numerator exactly. So I have 10 y's in the top and bottom. I can cancel those off, and all that's left is the 3/4. So kind of messy at the start, but just with a couple different steps of combining, a lot of stuff was able to be reduced away, and we got quickly down to that 3/4. Alright, let's go ahead and look at another example. This time we have a fraction to a power, or a quotient to a power. And on the previous page we did have a quotient to a power rule that said, if that is the case, take your numerator and raise that to the power. Take your denominator, raise that to the power. And then now you have power to a power, so you multiply exponents, x to the 8 and y to the 20. Sometimes there's a temptation on people's part to look at the 8 and the 20 and see a 4 and decide to cancel that. But you have to remember there's not actually any 4's in the numerator. There's 8 x's. And there's no 4's in the denominators. There's 20 y's. So this 8 isn't a factor, so its factors, 4 and 2, are not factors of the numerator. The 8 is telling me how many factors of x I have. The 20 is telling me how many factors of y I have. So exponents cannot be reduced like we could reduce the 6's in the 18 and the 24. Alright, continuing on with some more examples of simplifying involving exponents. So here we have a fraction that's raised to a power, so we could use the quotient to a power rule and raise the numerator and denominator each to that power. But in the numerator we have 1, 2, 3 factors, and in the denominator we have 2 factors. And the product to a power rule says if we have 3 factors raised to a power, each of those gets individually raised to that power. So what I would usually do with this is apply both the quotient to a power and product to a power rule simultaneously and say that in a fraction like this made up of all multiplications, that the exponent gets distributed to every factor inside, so to the 5, to the x, to the y to the 4th, to the 7, to the y or w cubed. So writing that out, going through each one at a time, I get the 5 squared, I get x squared, I have the y to the 4th squared, the 7 gets squared, the w to the 3rd gets squared. So again, every single factor inside of that parentheses gets that exponent distributed to it, and that is actually using both the quotient to a power and the product to a power rule simultaneously. And then I would just start simplifying. So 5 squared, 25, x squared is already simplified. Here we have a power to a power, so I'd multiply y to the 8th. And then just moving down, doing the same steps in the denominator, 7 squared is 49, and power to a power here, so w to the 3rd raised to the 2nd would be w to the 3 times 2, or w to the 6th. And none of our bases are the same here. This is all 5's, this is all 7's, x's, y's, w's, nothing in common, so that would be as simplified as we could get there. We've removed parentheses, which is one of our requirements, and we've carried out the exponents on any numerical factors. When we look at part F, at first it looks similar, and you might think I'm going to take that 2 and distribute that to 1, 2, 3, 4, 5, 6 different factors. The important thing to see here is that the parentheses are only on the numerator, so that 2 only applies to the numerator. So I would distribute that to each of the 3 factors there and get 4 squared, x to the 5 squared, y to the 8th squared, but that's where that distribution of the 2 ends because the bottom was not involved in that parenthesis. So I'm just going to copy the bottom. And I'm going to work out the top, and once I get that simplified, I'll deal with simplifying across the fraction bar. So the 4 squared is 16, power to a power, so we multiply x to the 10th, power to a power, so we multiply y to the 16th, and again the bottom I'm just copying, 8, x to the 8th, and y to the 9th. And then I want to simplify by removing any common factors, and I see an 8 in common here, so I'm going to show that. That's 2 times 8, and I have the 8 on the bottom, so I'll cancel those off in a minute. When I have the same base, you could use the subtraction rule. You could also think of it as if there's 10 x's up here, that means you could split that into 8 x's and 2 x's. And then on the bottom I would have 8 x's, and I'm revealing how many they have in common, and so I could just go ahead and cancel those off instead of thinking about the subtraction rule. I'll mention the subtraction rule would work as well, but this is kind of the way I think of it mentally usually. If I looked at this, I'd think these 9 y's are going to cancel 9 of those y's, and there'd be 7 left over. But just to show you that, y to the 16th has 9 y's like there is in the bottom, but there's still another 7 to make up that total of 16. And then I have those 9 y's in the bottom. So if I write it that way, then I can see all the different things I want to cancel, the 8's, the x to the 8ths, the y to the 9ths, and then I can think about, alright, so what's left over? And I would have the 2. I'd have these 2 x's, or x squared, and these 7 y's, or y to the 7th. And everything in the denominator cancels, which means there's still a 1 there, but we don't consider a fraction to be simplified when we write it over 1, so I would just write it without that. And it's also very common for me, if I'm at this step right here, to just jump down here to that answer and not write out those common factors, but just think about them. So I might say 8 goes into 16 twice. These 8x's cancel 8 of the 10, and that would leave 2 left over. These 9y's would cancel 9 of these, and that would leave 7 left over. So it is possible to do that in your head rather than writing it out. You decide what's more comfortable for you. And then you also could have used the subtraction rule, x to the 10 over x to the 8. You subtract exponents, so x to the 10 minus 8 is x squared. Y to the 16th over y to the 9th, we would do subtraction, so y to the 16 minus 9, which is 7. I don't like doing that purely as just a rule. I like to think about it. There's 16 y's up here. 9 of them will cancel with this, and that would leave 7 left over. That's a little bit more logical to me, and I prefer to think about it in that logical manner rather than just trying to execute a rule. Alright, one final example, and this one is an application, so let's go ahead and take a look at that. The weight, f of d, in ounces of a thick crust pizza with 3 toppings at Papa Del's is described by the equation f of d equals 0.41 times d squared, where d is the diameter in inches of the pizza. Estimate the weight of such a pizza with a diameter of 12 inches. So let me go ahead and copy the function down here. F of d equals 0.41 times d squared. And then let's think about what they're asking us for and what they're giving us. They want us to estimate the weight, and it says up here the weight is f of d. So we're trying to figure out the f part of this equation. And then they provide us with the diameter of 12 inches. So that would be d. It says here the diameter is d. So they want us to figure out the weight when d is 12. So they want us to figure out f of 12. And we would do that by plugging the 12 in. So 0.41 times 12 squared. And one way we could do that is do a little work in our head. If we take the 12 and square that, we would get 144. And then at this point, I would go ahead and just move over to the calculator. Let me bring that in and just do that multiplication. So 0.41 times 144 is 59.04. And in an application like this, we should always put units on our answer. So we have to think about what it was we were trying to find. We were trying to find the weight, and it says that the weight was measured in ounces. So this would be 59.04 ounces. And that would be our answer. I'm just going to go ahead and mention one other quick thing on this. Once you plug in the 12 into the function and you get to this point, it wouldn't bother me at all if you went to the calculator right then and jumped across to the answer. So let me just go ahead and show you what that would look like if you chose to do that. You do the 0.41 and then times 12 and then just raise that to the second power, and that'll take you straight over to your 59.04. Okay, that's it for this section.